The next set of functional groups we'll go over are the aldehydes and ketones. The general formula for an aldehyde is RC double bond OH, and the shorthand notation for this is RCHO. The proton at this position is not acidic. You would have a difficult time even finding a pKa value for that proton. And if you think about what the conjugate base would have to look like, you'd have a lone pair on this carbon. It would not be resonance stabilized because this oxygen already has a complete octet, so it would not be a stable conjugate base. There is a dipole, of course, going towards the oxygen, and additionally there is a resonance structure that looks like this, and so those two things together cause the carbonyl carbon to have a partial positive charge and the oxygen to have a partial negative charge. Ketones behave similarly to aldehydes, and that's why we kind of group these two together. The difference, of course, as you can tell, is that there are R groups on both sides of this carbonyl in the middle. If the R groups are identical, we say that that's a symmetrical ketone. If they are different, we say that's an asymmetric ketone. Once again, because of the dipole moment and because of the resonance of the carbonyl, you have an electron-deficient carbon and an electron-rich oxygen. As far as intermolecular forces go, you have dispersion, of course, that will take place with aldehydes or ketones. You do have dipole-dipole interactions because of the polarized carbonyl, the C double bond O, that can interact. However, you have a hydrogen bond acceptor, but no hydrogen bond donor. And so you will not have, between two molecules of an aldehyde or ketone, you will not have an H bond. However, it will not H bond with itself, but with a donor. So for example, if you put an aldehyde or ketone in water and there was an H bond donor present, then you would see an interaction, a hydrogen bonding interaction between the ketone or aldehyde and the water.